Hello friends, welcome back to my YouTube channel MS Maths. In this video, I will discuss the stream tube. The concept of stream tube in fluid dynamics, it is very important to understand the flow field of the fluid. So, we can take an example of the magnetic field. In the magnetic field, there is a magnetic field line, or in a electric field, there is an electric field line, or we can say that in an electromagnetic field, there will be a electromagnetic field lines. So, in that field, if we take a flux, okay, so I say it is a magnet, and you know the magnetic field line like this, magnetic field line like this, like these are magnetic field magnetic field lines. And if we take a flux, or basically we can take a small area, like through the like number of magnetic field lines will be passing throughout that region, we'll call it flux. Okay, so in the fluid dynamics there will be streamline. We have studied about that streamline in our previous lecture. So firstly, I suggest you that if you want to continue with this video, so you should have at least that much sufficient knowledge of the streamline, streak line, and path line to understand this lecture. Okay, so now in this video we'll discuss the stream tube. So basically, what is the streamline? A streamline is a line. Okay, streamline is line which is basically based on the position, based on the like uh, in the case of line, it is basically dx by u, dy by v, and dz by w. That is the equation of streamline. But streamline is nothing but a line where the tangent to the instantaneous velocity. Okay, so basically streamline is a line where the tangent is the it is like the line which is tangent to the instantaneous velocity field. Okay, this is called a streamline. Okay, so it is a streamline which is the tangent to the flow field. Now, in this case, we consider a stream tube. So basically, we take a area that is A1. I say it is A1 and it is A2. Okay, no, we will consider a flux. Okay, so the volume or the fluid passing through the area A1, passing through the area A1, that is I say rho 1, and velocity which is V1. So it is rho 2 and V2. Similarly, the total force to this will be rho 1, A1 and V1. And similarly, rho 2, A2 and V2. We can use the same concept of the magnetic field or electromagnetic field, or we can use the same method to visualize the velocity by introducing field. So the velocity introducing field lines. This is a field line, which is a streamline. Okay, this is a field line. A stream tube is a tube. Stream tube is a tuber region, or a region in the shape of tube of the fluid surrounded by the streamline. These all are like red lines are known as it's called the streamlines. And streamline do not intercept each other. This is the very important property. These lines do not intercept each other. It passes through the stream tube with all points along its length. I say it is a stream tube. Okay, it is a stream tube. You can see here these line passes through the all points. Okay, here is also a stream line in between this. So it passes through the all type of all type of points on all the points along the length, but it do not intercept each other. This is the very important point. Now next, it passes through the streamline, and let's take two cross section stream tube, two cross section areas of the stream tube, that is A1 and A2. I have discussed already. If these areas are small enough, that fluid velocity across the cross section will be constant. Basically, these area are small. Like in the fluid concept, if the area is a area through passing the fluid, area in which passing the fluid, if it is a small, then velocity will increase. Like there is area, it is very high, it is a high area, or it is a big hole in a pipe, or you can say. Now next will be small. So from here to here, the velocity of the fluid will increase due to small area. In this case, we have taken in this in such a manner that first is a small area and second one is a greater area than small, like first one. So in this case, the velocity will be constant. It will not increase or decrease. Okay. So this is the concept behind this. So we have taken area. We have taken two cross section area, that is A1 and A2. Okay, let's assume the velocity is v1 and v2 of the fluid at the cross section v1 and v2 respectively. The rate of which fluid is containing, rate of which fluid is containing stream tube, containing in stream tube is rho 1, rho 2 and rho 3. Basically this is a rate and at which the second cross section, that is rho 2, v2 and a2. Now in if the fluid is incompressible inside the stream tube, basically the fluid which we have used in the stream tube, it is incompressible. Incompressible means that if the mass is not changing through the time, so if the mass will not change, then density will not change also. So in compressible fluid, the rho 1 and rho 2 will be equal. Now if the rho 1 and rho 2 will be equal, I can say that rho 1 A1 and V1 is equals to rho 2 A2 V2, because the velocity or the rate of the both the cross sections will equal to each other. Now in this case, rho 1 equals to rho 2, I say it is rho. So basically we can consider or we can write as A1 V1 is equals to A2 V2, and we can write V1 upon A2 which is equals to V2 upon A2. Now there are two different ways to describe the field flow. So this is basically the relation between the basically tuber region, or in this case we'll discuss two different fluid flow method or description about that method. One is the Lagrangian description and other one is the Eulerian description. We'll discuss it in very like in the simple way that in general I will start with the fluid containing or like fluid flow in a river, and okay, so now there are two approaches to understand the fluid flow. First is the Lagrangian specification of the flow, and second one is the Eulerian specification of the flow. Now whole description I have written in these notes. I will just explain what is the concept behind these approach. In the Lagrangian approach, the Lagrangian description is one in which the individual flow particle are traced. Okay, there is a fluid flowing inside this river, or basically I say it is some like fluid which is flow in such a manner that will trace in Lagrangian approach. We will trace the fluid particle, individual fluid particle. We'll study on individual fluid. I say it is a particle, and I will study on the properties like velocity, its position, its like its pressure and all the things. So we'll discuss only on this point also, only on this point. And also same as in the fluid, like that is a like basically we know that in a fluid there are so many particles we can't count, and we can't assume the individual particle. But in hypothesis, in Lagrangian approach, we will take a particle, and the tracing, like by the tracing of that particle, I say the particle moving in this way, in this such a manner. So the first time, like at a time t, particle is here, at a time t plus delta t, particle here, like time t plus like 2 delta t, particle is here. So we'll discuss or we will we will research on only individual particle. One by one we'll discuss for all the particle of the fluid. So this approach is known as Lagrangian description. So the Lagrangian description in which individual fluid particle are traced, in this approach of the fluid flow of the like particle is used as a marked. Okay, we will mark the particle, and the position and velocity describe a function of time. The position and the velocity, obviously it is a time, like function of time, and after some time the position and velocity will change for that particular particle. So in that case we will study for that particle only. Okay, as the particle moves in the fluid flow, their position and velocity will change with the time, because it is a like function of time. and the physical laws such as Newton's law, conservation of mass and energy, apply directly with the particle. These types of law to study the properties of that fluid flow, we will apply on that particle. If there are only few particles to be considered, this approach to be desirable. Basically, in a fluid particle, in a fluid, I know, and we also know that in a fluid particle, there is no countably many points. There are incountably, infinitely many points will be there, infinitely many particles will be there. So we can't assume one by one or individually in that fluid. So this approach will use rarely. If there are only few particles to consider this approach to be desirable. However, fluid flow is a continuum phenomenon. We know that it is a continuum phenomenon. It is a like we know that particles are discretization, but in the case of fluid flow, we will consider as a continuum, as a continuous. So it is known as continuum hypothesis. I have already discussed it, like it is in my previous lecture, and it is not possible to trace each particle individually in a complex flow. Okay, in a complex flow field. Thus, this method rarely used in a fluid dynamics. Because of that, fluid is a like fluid follow the continuum hypothesis or continuum phenomenon in the fluid. So we can't study on a particular particle of a fluid. Now, next one is the Eulerian approach. In Eulerian approach, one which in a Eulerian approach, one which the control volume is defined with the flow properties expressed as the field in the fluid flow. Basically, in this case, we'll take a volume. We'll take, like, instead of taking the particle, we'll take a volume, and this volume, obviously this particular set of some particles, we will call it a volume. So after some time it will be here. Okay, after some time it will be here. So it is easy to consider that volume instead of a particle. Okay, so in the Eulerian approach, we'll consider a control volume in which contour is defined, in which the contour or the domain which we will take a particle or we will take a volume from this particular section only. So in which contour is defined, in which the fluid flow property expressed. In the approach, the individual particle are not identify or like not need to identify or not need to trace individually. Instead of these instead of like there is a typo, it's identify, and instead of these the control volume consider pressure, velocity, etc. All the properties we will check on that particular volume, not only that like particles. Okay, now all other fluid properties are described as field, which is in the control volume. It means each property is expressed as a function of space and time. In that particular manner, in a particular approach, that Lagrangian approach will take a position and velocity, the function of time. In this case, we will take a like basically a volume, which is a like three-dimensional quantity, in which we take the function of time as well as space. Okay, so this is the concept, and either the Eulerian and Lagrangian, either the Eulerian or Lagrangian description of valid in fluid dynamics is usually different. Okay, so these are two approaches to understand the fluid flow in the fluid dynamics. Now, how can we like relate both the both the fluid flow method or both the fluid flow description? So there is a total derivative concept, or there is a subset like a material derivative, which is a nothing but a bridge in between these two approaches. It is a useful bridge between, it is a useful as a bridge between these two approaches. This derivative for some quantity is defined as the rate of change of the quantity following a fluid particle. Okay, a quantity, basically that quantity, like it can be pressure, it can be velocity, and etc. That is a property, that is a quantity, is defined as the rate of change of the quantity following a fluid particle, which is basically the property which following by the fluid particle. Now, what is in the approach and what is the basically the meaning of the material or total derivative or substantial derivative? Now, consider, suppose a fluid particle moves from p x y z t because it is in a 3 dimension and also it is a function of t at time t, and after delta t time it is at p dash. So the coordinates are x plus delta x, y plus delta y, z plus delta z, and the time like basically the time coordinate will be t plus delta t will be there. Let a function phi, which is a scalar function associated with some properties of fluid, like delta f vector is equals to del f vector upon del x into del x, delta x, plus dou f vector upon dou y into delta y, plus dou f vector upon dou z into delta z, plus dou f vector upon dou t delta t. Now, if the derivative will be like where the derivative with respect to t, so it is nothing but delta f vector upon delta t, which is equals to dou f vector upon dou x delta x over delta t, plus dou f vector upon dou y delta y over delta t, plus dou f vector upon dou z, then delta z upon delta t, plus dou f vector upon dou t delta t upon delta t. Now, the limiting value df vector upon dt is nothing but the limiting value delta t tends to 0, that is dou f vector upon dou t. So it will be dx by dt dou f vector upon dou x plus dy by dt dou f vector upon dou y plus dz by dt dou f vector upon dou z, plus this one will cancel, so it is nothing but plus del f vector upon del t. So q vector will be, so q vector is nothing but a velocity vector with the component u, v and w. So df by dt, it is nothing but u dou f by dou x plus v dou f vector by dou y plus w dou f vector upon dou z plus dou f by dou t. In this case, we'll consider that we can write in this way df vector upon dt is equals to q into, so it is nothing but that q is a vector quantity and f is also vector quantity, so it is the dot product of del f vector, okay, plus it is a remaining, so we can add dou f vector upon dou t. In general it will be d by dt is equals to dou by dou t plus q vector into delta. Now f is nothing but a particular quantity. There may be like function f or phi or anyone, any other property or any other quantity will be there. So in general we can write in this way, in this manner. So it is nothing but the general formula of the relation between the Eulerian and Lagrangian. So it is nothing but what is the significance and what is the meaning? Okay, let's see. Basically, if here d by dt refers to the total particle rate of change. Total, it is nothing but total differential following the fluid. Total differential following the fluid. And q vector dot delta refers, it refers to the conductive fluid or velocity of moving fluid. Okay, moving fluid. And at last, dou by dou t refers the local rate of change at a point in fixed space. At a point in fixed space. So it is nothing but the physical significance of this particular generalized formula. So this is all about the tube, okay, stream tube, and I hope you understand the concept of the stream tube and the concept of the basically the total or material derivative. So thanks for watching my video. Keep watching MS Maths for these types of video. For like you can subscribe the channel. So please subscribe the channel, share with your friend. Thank you. Bye bye.